the last thing is to obviously calculate the resistance to have power on the output at 1 watt. And we're going to find that resistance by doing R is equal to V out over I out. Okay, ohm law. And this is going to be 5 divided by 0.2, and that is 25 ohm. So that's the resistance we need across the load to maintain this current and that power. So if you reduce this resistance, this current is not going to be able to maintain, and that ultimately need to increase here. But because we've already sized our inductance based on that, so which means you're going to start stressing your inductance, the ripple current is going to increase, and that means your inductance here is going to start reaching saturation, because that is another part that is very important. You need to make sure that the inductance does not reach saturation based on the peak current. So in this case here, the peak current, I peak is basically equal to I in plus the ripple current divided by 2. This is your peak current. So make sure that the peak current does not exceed the inductor saturation current. Because if your peak current is higher than the saturation current, based on this design, your inductor is going to reach saturation, which means when it reaches saturation, the inductor is going to start, the inductance is going to start dropping, and that's going to increase power losses, and your converter is going to stop operating. So never exceed the peak current. So make sure you choose an inductance which is saturation current that's at least 20% above your inductor peak current. You can calculate this inductor peak current here. It's very simple. Where is our ripple? We can calculate this quickly. So it's basically the input current 0.47 plus the ripple current is 0.141 divided by 2. So it's 0.54 amps. So that's our peak current. So if we spec our saturation current to be 20% above this peak current, we're going to multiply this by 1.2, and that's going to give us 0.65 amp, which means you have to choose the inductor saturation current that must be at this rating current 0.64. Now if you choose an inductor with a saturation current that's lower than this, that means your inductor will saturate in this design, and it's going to cause more problems for you. Okay, now before we end this tutorial, let's quickly change the parameters here and see whether we're going to get a 5 volt. So we need to change here to a 10 micro, and here our switch, we're gonna operate at 100 kilohertz. The duty cycle or pulse width is 50%, okay, and it's gonna be 0 and 5 volt, initially starting at low and then it pulse to high 5 volt. We say okay. Then here our inductance, we calculated it to be 100 micro because we cannot get the 89, so it's 100 micro Henry. So this is about what we have for this design. Okay, now if we run it, there we go, and as you can see, we have 5.4 volt, okay, as designed. We designed it for 5 volt and we got about 5.4. Now this is a simulation, so we assume there are no losses here. So I'm sure if you design this in a real, you choose all these parameters in a real circuit, you've got 100 kilohertz frequency here, you're going to get just about 5 volt because there will be some power losses here. Look at the output current, 0.22. The input current, 0.47, it's about 0.5 fluctuating. So that's basically how you can design for any output. Now you can choose to have 9 volt here. You go through the same calculation again. You're going to find different parameters that will give you different values for your inductor. Okay, so now if we change, now let's say we change this resistance, we reduce it to 10 ohm. Now 10 ohm, it means that we're changing the output current. So that means the output current is now going to be 5 divided by 10 ohm. Okay, so we basically I out is V out divided by 10 ohm, and that gives us about 0.5 amps. Now 0.5 amps here clearly goes about our design specification of 0.2 amps. So which means everything we've done here is now going to have to be changed. But if you are operating with the same parameters here, your circuit is going to be stressed. So let's test it out. Okay, now look at what's happening. Now we're still maintaining 5 volt because it's a simulation. But look at the input current, it's 1.3 and the output is 0.5. Now, this here will not work if it was a real circuit. It's only working because it's a simulation. In a real circuit, this inductor is going to start to saturate because your ripple current is going to increase your saturation, which your peak current and all of that, and yeah, the circuit is gonna stop working. Great stuff. So that is it, guys, for this tutorial. We're going to stop it here, and this has been quite a step-by-step guide into a boost converter design. The steps here can be applied in real applications, real design, and you're going to be converging the result as we've done them here in the simulation. Thank you for watching. If you found this useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. Until next time, cheers.